Let's continue. So, what does the EH axis signify on the Pobe diagram or on the EH-PH diagram? So the EH, the redox potential axis, is actually based on the standard hydrogen electrode potential scale, and it is designated an EH. So what does this mean? The redox potential of a system represents, most importantly, its ability to affect electrons, okay? Either to supply or to remove electrons. So you find that if the system tends to remove electrons, then the potential is actually greater than zero. And then oppositely, if the system tends to supply electrons, then potential is actually less than zero. Okay, so these are actually reducing conditions, and if you are removing electrons, oxidizing conditions. Okay, how about your pH axis? The pH axis describes the ability of a system either to supply protons or to remove protons. Okay, so in acidic conditions, we know that the proton concentration is quite high. And then in caustic conditions, we know that the concentration of protons is actually low. The hydroxide concentrations are actually quite high in caustic conditions. Okay, so usually a large amount of different species exist simultaneously in an aqueous mixture in a fixed EH-pH conditions. And the Pobe diagrams, as we said before, it only shows the predominant species in which have the highest concentration in each area of stability. Okay, so in some areas, you say in acidic conditions, there are some species that actually favor a high proton concentration. Okay, and that they are actually more stable in those. And then there are also species that actually favor reduced proton concentration, and they exist very well in alkaline conditions. Okay. Now, what is the effect of potential on the stability of species in the solution? So this y-axis is your potential axis. So what happens when you increase the potential in a system? Okay, so when you increase the potential in a system, remember we are saying we are moving into the oxidation region. Okay, that is the region usually above zero, oxidizing conditions. So in this region, we are saying that there is loss of electrons. And if there is loss of electrons, it means that we are favoring a leaching or metal dissolution in this case. Okay, so we say that the system is actually more oxidizing when you are increasing because you're going into the oxidized region. So the ratio of your oxidized species over your reduced species actually increases. Okay, so that's the effect of increasing potential on the system. How about if we reduce the potential? So when we reduce the potential, we are saying that the system is now in more reducing conditions. And here we say the gain of electrons is actually favored. So if gain electrons is actually favored, it means that you're moving in from your aqueous ions to your solid state. So metal deposition is actually being favored. For example, you're moving into Fe0 from Fe3 plus, Fe2 plus to Fe0. So when you now increase the pH, you can favor metal hydroxide precipitation in this if you increase pH going in this direction. But however, I want you to understand that when you increase or decrease your potential, you are actually creating either oxidizing or either reducing agent. You're actually creating either metal dissolution or metal deposition. You need to understand what is the effect of increasing or decreasing your potential on the system, on the stability of the species that are in solution. Okay. Now, let's look at this EH-pH diagram for ion and the water system. So you see that there is Fe3 plus here, Fe2 plus, Fe0, okay? And you've got your oxides or hydroxides here when you increase your potential. look at mainly using these three regions here. So region number one, this region here, is where your ion is in it's in ionic state Fe2 plus or Fe3. So that's, let's call it this region number one. Then there's this one, region number two here, where you have your Fe0 in solid, that's region number two. And then the last region is this one here, the last region where you've got your oxides or your hydroxide. That's your region number three. Okay, so we can confirm and say that this region is actually a corrosion region, because if you put iron in such conditions, then it is actually going to corrode. It's actually going to go into solution. It's actually going to be mass transfer from solid into aqueous state. So there's going to be corrosion. Okay, so that's a corrosion region. Now, what happens if you increase the potential? Let's say this pH 3 or 4. What happens? You actually move into a region where you call what we call anodic passivation. Okay, so you actually passivate the ion, and it does not corrode because you form a passivation layer of your hydroxide or your oxide. Okay, how about in this other region, the third region? This region is actually the region of cathodic protection. So if your ion exists in this state, then it is cathodically protected and it will not corrode. Okay, so region one here is the region whereby there's going to be corrosion. Region number two is actually no corrosion, but is cathodic protection of your ion. And also region number three, there is anodic passivation, and therefore no corrosion of your ion. Okay, so we can call these regions again. Region number one, corrosion. Region number two, immunity. And then region number three, we call it the passivation region. Okay, so anodic passivation or protection is the reduction of corrosion of a metal by polarizing it into its passive region and maintaining it in that region. So that is anodic passivation. So you can control the corrosion of a metal by controlling the electrode potential in a zone where the metal is passive. So this is the anodic passivation region here. Okay. And for the cathodic protection, you can also reduce the corrosion of a metal by polarizing it into its immunity region and maintaining it in that region. Okay, so here, this is your immunity region where you have got your cathodic protection. Okay, all right.